Hello, I'm Chen Wang from Tsinghua University. I'm very glad to introduce PalmBoard leveraging implicit touch pressure in statistical decoding for indirect test entry. This work is in collaboration with Xinyi Yuanchun Shi from Tsinghua University and Xiaojun B from Stony Brook University. With the popularity of mobile devices like smartphones and smartwatches, touch-based text entry has become a common way for people to type. Even if the user made a mistake, the underlying algorithm can still predict the intended words, which is usually called input decoding. The most common decoding algorithm is based on Bayes' theorem proposed by Goldman. Just like the equation here, I refers to touch information, W is a word in library. In practice, researchers have derived two variations of the equation, the absolute model and the relative model. The absolute model treats each tab as independent by varied Gaussian distribution, so P I in the condition of W can be calculated according in both x and y dimension. The relative model, however, considers variations of two tabs as independent by varied Gaussian distribution. In order to provide statistics for the Gaussian distribution, researchers have explored touch model in different situations, like typing with 10 fingers on touchscreen, typing using one thumb, or even typing in the air. Noticeably, touch pressure is becoming increasingly popular on many devices. For example, writing on touchscreens, 3D touch on phones for some shortcuts, as well as the button on some headsets. There are also some works using pressure to input text entry on tablets, phones, and smartwatches. However, in most of the time, touch pressure is used explicitly, like to change the case of a character, to move the cursor, or to control uncertainty. To our knowledge, there is no existing work that uses pressure as implicit channel in text entry, which is a core part of our work. To demonstrate the significance of implicit touch pressure in text entry, we choose a one-handed typing scenario. Some of you may wonder why. First, one-handed typing is extremely useful when the other hand is not available, like occupied by food. It could also free the other hand for users for other interaction purposes, for example, to move the mouse. Moreover, although abundant literature has shown that users could transfer their muscle memory of two-handed touch typing into many different surfaces, whether they could transfer it to one-handed typing is not that clear. Next, I will introduce our work in three aspects shown here: examine one-handed touch typing behavior, improving statistical decoding algorithm, and finally evaluation. The first problem is how we model users' one-handed touch typing behavior. To explore this, we first carry out a user study. We use the sensor morph as a apparatus, as shown in the left picture. It can sense pressure ranging from 0 to 15 Newton, reports force image in dimension 185 multiply 105 with a frequency of 130. To retrieve the data, we connected to a laptop computer. The experiment was conducted in two modes called placed and hover, respectively. Participants could rest their palms entirely on the touchpad in placed mode, as shown in the right picture. For the hover mode, they must lift their hands and elbows off the pad just like we type on most touchscreens. In both conditions, participants were asked to perform one-handed touch typing to enter the target phrases. We are interested in whether resting their palms would affect the typing performance in these two modes. Here's a screenshot of the experiment platform. For each mode, there are 4 blocks and 15 phrases in each block. We provide asterisk feedback when a touch is detected to avoid affecting users' touching behavior. A total of 12 people, including 9 males and 3 females, participated in the first experiment. By analyzing the touch points, we found some very interesting results. We can see that from the point distribution that in both modes, the input signal is very noisy. Touch points of different keys overlapped, Comparatively, SDX is 1.6 of SDY, which means that the vertical dimension is more controllable for the users. Users can distinguish different rows more easily. SDX and SDY are smaller in place mode because the typing posture is more stable. We also explored the emergent keyboard layout. Generally, the distribution followed QWERTY layout. However, since participants typed the whole keyboard with only their right hand, the left part of the keyboard is often squashed. We proposed SR, a metric to present the squash extent, which is the distance of the centroids of key Y to P divided by that of key Q to T, shown in the left picture. SR close to 1 means that users view the touch area as a whole keyboard, while smaller SR means only half keyboard. According to our findings, SR differs a lot among users. It could range from 0.4 to 1. The two pictures in the right show two typical types of SR. The left user could type in a standard QWERTY, while the right user tends to condense the left part of the keyboard. As users only use 5 fingers to type all 26 characters, we also labeled which fingers participants use when they type each character. We found that everyone tended to use multi-fingers to type. They use even more fingers in place mode. The picture in the right shows average keys pressed by each finger. Larger ellipses indicates more keys. We can see that most taps are performed by index and middle finger. Based on our findings, it could be proved that muscle memory of two-handed touch typing can also be transferred to one-handed scenario. We now analyze the results on touch pressure, as it is a key part of our work. We use T to represent duration of a touch, which often contains a series of data frames, ST to represent the size of a tap, and Premax T to represent the maximum pressure in one frame. ST hot and Premax T hot is the maximum of ST and Premax T across all frames of a touch. We calculated the average of those values for 4 different rows on keyboards as shown in the table. We can say that the 3 metrics is significantly different across rows. T is longer in lower rows and size and pressure is smaller on lower rows, indicating that when tapping on keys on lower rows, users usually tap slower and lighter. These findings were extremely helpful for our algorithm part. I'll describe that later. Based on the data of our first experiment, we did a series of simulations to realize the algorithm on PalmBoard, as we allowed the users to raise their palms during typing. The first challenge for PalmBoard is palm rejection. The pipeline of our touch detection is shown here. For each image, we detect touch blobs according to the size and level of the pressure, and then construct touch events based on continuous frames. Palm touches were ruled out according to the average T, ST, and Premax T of the touch event. Then we performed 3 simulations to improve the classical input decoder iteratively. Specifically, we test different keyboard layout, keyboard model, and the significance of pressure data. We first ran the simulation on the collected data from Study 1 and used the McKinney and Sorev phrase set as a test set. I will focus on introducing the simulation results. For more details on the simulation, please refer to our paper. We first compare the by-key layout with QWERTY. By-key layout is shown here, which merge 2 keys, horizontal keys into one. Results show that by-key yielded higher top 1 accuracy in general condition, but the result is reversed in personalized condition. Here, general means that we merge the data of all users together and calculated accuracy together, while personalized means that we calculate accuracy person by person. The results indicated that by-key layout might compensate for the difference in touch point distribution among different participants, but the compensation is not enough for personalized use. Furthermore, as we mentioned before, some characteristics of implicit touch data are significantly different across rows. which can be used to predict which row users intended to press for each tab. In total, we use 6 pressure features shown here, including the XY position, the duration, etc., denoted as vector f. We then calculated the probability of each row for each touch based on the touch location and touch pressure and use them to predict the input word. The confusion metric proves the accuracy of target row prediction. F1 score surpassed 0.85 in both general and personalized conditions. And most errors only come from adjacent rows, which means that our algorithm can effectively predict the target of each target row of each tab. We then incorporated the information into the Bayesian decoding algorithm. Compared with the classical decoder, we introduced the F vector, which describes the characteristics in implicit touch pressure data. The equation is shown here in this slide. This detailed description can be found in our paper. The results here show that in general condition, the accuracy increased by over 5% after force was added. In the third simulation phase, we tested different keyboard models. As previous works suggested that users were more likely to exhibit a relative model, Markov process when performing eyes-free typing with muscle memory, which is consistent with our experiment design. Therefore, we further modified our algorithm to use relative touch points for input prediction, as shown here in the below. As the green line shows, relative model can improve the accuracy by over 10% than the absolute model. Based on the simulation, we choose QWERTY layout relative model with force as the algorithm of PalmBoard and carry out a second user study to evaluate its performance. We selected 2 other modes named rectangle and general as baselines. Rectangle mode is perfect QWERTY layout, occupies the whole touchpad, while general mode uses QWERTY layout with centuries of each key in the first experiment. Both of them used absolute algorithm and without adding false information. We choose the 2 models to explore the influence of layouts and false information. Platform and setup for simulation for this experiment are similar to experiment 1. The only difference is that in this time they have to perform real test entry tasks using 3 different techniques. Participants could swipe to reach the desired word and use thumb to select the word. Here shows the results of input speed. We can see that PalmBoard mode achieves the fastest speed with an average speed of over 32 words per minute. Expert users could even achieve 40 words per minute after practice. It was much faster than existing one-handed touch test entry techniques on smartwatches and close to one-handed typing on smartphones. And general mode was faster than rectangle mode. We also calculated the input accuracy using CER. PalmBoard also was still the best, with only 0.6%. Both the speed and CER proved the effectiveness of utilizing false information. Now, we made a brief summary of our work. We first explored the one-handed touch typing behavior and found many interesting results. Secondly, we improved traditional decoding algorithm by leveraging implicit pressure. And finally, we evaluated our technique and proved its effectiveness. Our work demonstrated that one-handed touch typing is quite promising and feasible, which can be used in various situations. Also, implicit pressure is very effective for decoding. We left more advanced pressure features for future work to explore. This is all my presentation. For more details in any part of work, please refer to our paper. Thank you very much for listening.